So hello, everyone. This is homework 10. This is a probability and stochastic processing, homework 10, question 1. So in this question, uh, it requires us to explain the following seven definition and the properties of the uh, of some stochastic process. And in the first part, it requires us to explain the Poisson process. And from the lecture notes, we have collected that the definition of Poisson process is listed as the following these three parts. And this is a probability matrix. And this is mean. Also, we can call it expected value. It is equal to lambda times t. And this is autocorrelation. It equals to lambda square t1 times t2 plus lambda minimum of t1 and t2. And so the definition and property and of the Poisson process, we know that the mean of Poisson process is lambda times t, which is a linear function of t, and the longer time we wait, so the expected number of buses is larger. Then we come to the second part, Poisson increment. This is the definition of Poisson increment, with xt is a Poisson process defined above and epsilon larger than 0. We construct a new process yt equals to xt plus epsilon minus xt divided by epsilon. This is a density, and this is expected value is equal to lambda. It's a constant. We know from this line. And the autocorrelation, we can divide it into two parts. One is the absolute value of t1 minus t2 larger or equal to epsilon. And the other situation is that one absolute value of t1 minus t2 smaller than epsilon. And and if we sketch the graph of the autocorrelation, we know that the area of this part is equal to lambda. So it doesn't depend on the amount of epsilon. So one epsilon goes to 0, the triangle becomes an impulse with area lambda also. We know that. Then considering the third part point impulse process, this is a definition. We make a differential with both sides. We can easily derive that the expected value is equal to lambda, and the autocorrelation is listed as this part. As this definition, we may define H as the output of a linear time invariant system with impulse both Ht and input as a Poisson impulse process. And then we consider the fourth part, the semi-random telegraph signal. This is the definition. One k is even and one k is odd. It's equal to 1 and minus 1. As this definition is constructed under the Poisson process, so from the definition Poisson process, we can derive the probability masses as I list in this line. And the expected value is equal to the exponential to the power of 2 times lambda times t. And the autocorrelation is equal to the exponential to the power of 2 times lambda times the absolute value of t1 times t2. And at this part, we know that the probability of xt equals to 1 or equals to minus 1 is not equal to 1 divided by 2. Because we start with 1. So as this line show, we know that the probability should be little higher than 0.5. Yeah. That's the semi-random telegraph signal. Here. And when the absolute value of t1 minus t2 is large enough, the autocorrelation is the amount of autocorrelation is extremely equal to 0. That means t1 and t2 are very far away. The xt1 and xt2 are uncorrelated. Then we consider the random telegraph signal. This process is a little like the how to say that? It's like the uniform processing. It is a definition listed as here, and the mean is equal to 0, and the autocorrelation is like the semi-telegraph signal. And we know that the probability is stationary is equal to the 0.5. So then we consider the random walk. The definition of random walk is we can define that as one torsion of a file called n times. K is the number of highs in n torsions, so the x nt is equal to k times s minus n minus k times square times s. So the consequence is equal to 2k minus n times s. So this is the probability message, and the mean is also equal to 0, and the autocorrelation is equal to the minimum of n and m times s square. So from the probability message, we get that when n goes to infinity, it's a little like the Gaussian density. and the autocorrelation function contains a term the minimum T1 T2. It also comes from the property of independent increments. Then we consider the second question, the Wiener process. This is the definition of Wiener process. It is constructed under the random walk. So the expected value is also equal to 0, and the autocorrelation is also like the random walk. So that's all.